Hello, I'm Philippos Papaphilippou and I would like to present to you my project for the summer of HPC 2017. The general topic will be an application that I developed that accelerates a specific physics simulator. First, we're going to have a quick overview of the HPC software we're trying to make faster. Simulations of lattice QCD has long been using a big proportion of the supercomputing resources. They are used by theoretical physicists to calculate the properties of the quarks and gluons, such as with the quark-gluon plasma, which requires extremely high temperatures to explore. Our specific applications is using some of the principles of lattice QCD for studying the electronic properties of carbon nanotubes. Carbon nanotubes are promising for many applications, such as in nanotechnology and computer processors. As we are going to see, the simulator uses leapfrog integration, which means the more steps we do, the more accurate the simulation becomes, but it also increases the simulation time. In our case, we can say that the percentage of the accepted trajectories is a measure of accuracy that it denotes the amount of useful work. The goal will be to fine-tune the number of empty steps so that the number of accepted trajectories will be approximately 66%. There are two approaches for tuning NMD: to change it statically or dynamically during runtime. And here we can see a simplified form of the algorithm that the fine-tuner will have. At each iteration, we calculate new trajectories until we have a small confidence interval that will guarantee that the measurement of the acceptance rate is accurate. Then we add this acceptance rate measurement to the list of all observations, and then we build a model. Using the model, we get a new prediction for the best NMD that we'll be using for the next iteration, with the hope that the overall acceptance rate will remain around 66%. Last, if the stopping conditions are met, the fine-tuner stops and the simulation continues using the last NMD prediction. In this slide, we can see a set of measurements for different number of MD steps. These kinds of graphs are useful because they can give a picture of what the model we are looking for should look like. The challenging is that during runtime we will not have as many data points as this graph for fast and accurate predictions. Finally, I will show you the NMD tuning in action. But before, I will explain what each graph will represent by using a screenshot of the video. Here, the upper title will tell which of the two states the tuning is using. If it is tuning, you will see that the green line is trying to fit the data. If it is measuring, we will see a new data point being inserted and repositioned until the measurements give a sufficiently small confidence interval. With the green dashed line, we will see what was the last prediction for the line. On the top right, we will see how the overall acceptance rate evolves during the tuning. The goal is to reach the green line, which is 66%. On the bottom right, we will see the number of steps that was used during the whole tuning. Thank you for your attention. Any questions will be welcome.